Orthogonal trajectories. Orthogonal means a curve or a line which is perpendicular to a given curve. Trajectories, of course, the path of curves. So curves which are perpendicular to a given curve are called orthogonal trajectories. Let's look at what we mean by orthogonal trajectory in a more exact way. Orthogonal trajectory is any curve which cuts every member of a given family of curves at right angles. So therefore, for example, y equals x is the orthogonal trajectory of the family of circles x square plus y square equals a square. X square plus y square equals a square represents the family of circles which have origin as their center and radius as a. So a line y equals x is perpendicular to each of the family of circles x square plus y square is equal to a square. How many circles are there which can be made of the form x square plus y square equals a square? Well, there are infinite. Depending upon the different values of a, different real number values of a, you can have infinite number of circles. And this line y equals x is perpendicular to each of those circles. What do we mean by a line being perpendicular? Well, this line y is equal to x is perpendicular to the tangent to the circle at that point. So for example, if we have the circle like this and a tangent is drawn to the circle, your orthogonal trajectory would be perpendicular to the circle at the given point. So this is the simple idea behind orthogonal trajectory of curve. And so in fact, the lines, not just y equals x, any line which passes through the origin is the orthogonal trajectory of this family of circles. So as you can see in this diagram, the red colored circles are the given family of curves, the given family of circles which have their center at the origin. And you see blue colored lines, each of which are passing through the origin. So each of these blue colored lines is the orthogonal trajectory to the family of circles x square plus y square equals a square, which are given in red. In fact, this is a very representative diagram for vortices, eddy current formation, a lot of flows in fluid dynamics, some phenomena in electricity and magnetism, and so therefore this is a very important and a very practical application of differential equations. So how does differential equations come here? Let's take a look. Let's take a look by directly learning how to construct or find out the orthogonal trajectory of a given curve. So suppose we are given a differential equation, or we are given the equation of a curve in the form of a function containing x and y and some arbitrary constants, which means that the differential equation is solved and we have the equation representing the curve. For example, x square plus y square equals a square is the equation of the family of circles for each of these red circles. So depending upon the different values of a, you will get different circles. So this equation is given to us, and so we start off with that. Step 1 says obtain the given family of curves, say f of x comma y comma c equals 0, where c is an arbitrary constant. What do we do with this? Well, in step 2, we formulate a differential equation by doing what? By eliminating the arbitrary constant. Formulate the differential equation representing the family of curves in step 1 by eliminating the arbitrary constant. So you eliminate the arbitrary constant and you will get a differential equation. What do you do with the differential equation? Well, you know that dy by dx represents the slope of tangent to a given curve at any point, which means if dy by dx has some value, then the equation of a line which is perpendicular to this curve would have the slope minus 1 upon dy by dx, or rather minus dy by dx, because the slope of the curve at some particular point times the slope of the tangent at that point should equal -1. The slope of the curve is given by dy by dx, and therefore the slope of the tangent this is the slope of the tangent. What I mean is the slope of the trajectory is equal to -1, and so therefore we get the slope of the trajectory is equal to -1 over dy by dx, or you could also write it as minus dx by dy. And so this is the expression that you require, and now you get a differential equation by doing this. Replace dy by dx by minus dx upon dy in the differential equation which we obtained in step 2, and solve this differential equation in the next step. The solution of this differential equation, once we replace dy by dx by minus dx upon dy, we get a different curve. Of course, we will not get the same curve that we started out with. What is the speciality of this curve once you solve the new differential equation? Well, that curve represents the orthogonal curves to the first and the original curves. So therefore it's a 4-step process. First you form the differential equation, or rather you write the equation of the curve representing the family of curves which are given to you. Then you form the differential equation by eliminating the arbitrary constants. In the third step, once you form a differential equation, of course you're going to get arbitrary constants, dy by dx, along with arbitrary constants. So you're going to have to replace dy by dx by minus dx upon dy. Again, you'll get another differential equation. Solve the differential equation, you'll get the orthogonal trajectory of the curve.